Hey, so don't forget about our huge and unprecedented Algebra Day celebration. So you can go right after class and eat. All right. I told them, so it's in A300, next to the cafeteria there in the one main building. And I told them specifically to hold back pizza for us. So when we get there, so there'll still be pizza available. And there's other stuff too. There's also games, so the games are kind of fun. And as I mentioned to you, I'm playing Wheel of Algebra. So if you want to come play Wheel of Algebra with me, you can do that. And there are prizes for that. I thought I'd give you a little bit of a preview of Wheel of Algebra here. Okay, so it works like Wheel of Fortune. So I'm sure all of you have seen Wheel of Fortune before. All right. So here I have a puzzle, okay, and now how Wheel of Algebra differs from Wheel of Fortune is all of our puzzles are going to be math phrases, all right? I don't think they have math phrases that often on Wheel of Fortune, right? So, but our puzzles are going to be math phrases. So this is a common math phrase. Actually, we're going to use it today, okay? So that's why I picked this one. For us, and all right. So now at Algebra Day, you'll be playing this in teams, of course, in individuals. But here we'll have to play it as a class. So you know how Wheel of Fortune works, right? You have to pick a letter for me, okay? And then you can buy vowels, right? All right. But normally you'd pick a consonant. Someone want to try a consonant here? Hope I can remember where everything's located at. So, yeah, Arthur. Y? Yeah, I don't think there's any Y there, all right? But that actually is a good guess because, remember, these are math phrases, right? So math phrases often have unusual letters that don't appear so frequently in, in just regular everyday phrases, right? All right, so no Y. You got to try something else. C, okay, yeah, now that's a good choice, right? So you know to make that, Nadine, because that is a frequently occurring letter, right, in the English language. But again, this is a math puzzle, so it doesn't no C there, okay, if I'm thinking correct, all right. All right, so yeah, well, you have to get some consonants before you can buy a vowel there, okay? So S, yeah, so there is one S, all right? So there is an S there. All right. So, Joshua, can you solve that? All right. All right. So you're right, Nadine. Okay. It's solved for X. Now, normally when you're playing, Nadine, you don't get to try different combinations, right, like that, right? Okay. When you're making a guess, it couldn't have been solved for Y, right? Because we'd already tried Y, right? Okay, so yeah, so that one was solved for X. All right. Anyway, that's the idea of Wheel of Algebra. All right. So they're all phrases that you're familiar with. So it's not impossible. All right. Okay. So today we're going to cover some new material in the notes, but I wanted to start here by looking first at your homework that's coming up due. It was actually due today, but I set it back a little bit, so it's due on the 18th, which is, what day is the 18th? Friday. So it's due on Friday. So that's a little bit unusual due date, right? So keep that in mind, right? Due Friday. So, and I wanted to show you a few things out of this. So let me see if I can get this one started here. So some of these things that are in this homework we're going to talk about today, all right? But to help you with the homework, but you will have noticed that the homeworks often begin with some simple little algebra exercises that are really review exercises from your prior algebra classes. So this is just to keep your basic algebra skills tuned up, right? Okay. So this is not something that we've been talking about in class. This is something that you would have done in a previous algebra class, right? Just adding these two algebraic fractions together, right? And these are easy to add together, correct? Because they have the same denominator, right? So when you're adding fractions with the same denominator, you just simply combine the numerators, right, and keep the common denominator. So this one is really easy to do, right? You're going to end up there with just 8, right? Because you're going to add the numerators there. So let me see if I can type this in. If I type 8, yeah, it'll do it right, okay? So in the numerator, you're going to get an 8, right? And in the bottom, of course, you're just going to get 5 plus y, right? Because you're going to keep that common denominator. So those are not things there that we've been checking, right? Okay, I mean, we've been doing in class, but they're just to prep you. All right, that one's a little bit harder, right, because you're going to have to find the common denominator, correct, and build up each fraction so it has the correct denominator. So if you're stumped on this one, if this is something that you've forgotten about from your beginning algebra class, remember you can always ask for the question help, right? Okay, so if y'all haven't discovered the help yet, I'm sure you have, but if you haven't, then you can look for the question help, right, and it will help you see how to solve, add those two fractions together. Now you've done that in the past, right? But that's something that may not stay fresh with you, right? Okay, from one class to the next. But so we do need to review it because sometimes we do have to do that. Okay, so if you're wondering, where did these problems come from that are at the beginning of these exercises, then they're just review problems, all right? Now, there are several problems like this there are several problems like this one in this homework, okay, where they're giving you a function. Most typically, it's going to be a linear function, and they're going to ask you either for the x or the y-intercept. It's easy to find the y-intercept, right, for a function. That just means you plug 0 in for x. But to find the x-intercept, you do the opposite, all right? So we haven't talked about that too much, but we have mentioned it. But it's going to come up in several problems in this homework, right? So to find the x-intercepts, just set the function formula to 0, right, okay? And then you have to solve an equation. So a lot of problems in this homework are going to be devoted to a lot of the problems in this homework are going to be devoted to solving equations. So we're going to look at solving lots of equations today. Okay. Another thing now that you may be asked to do once you find the x-intercept, right? Okay. Once you find the x-intercept is to interpret that. All right. So what is that x-intercept telling you in this particular context? Now, in general, the x-intercept tells you, what input x gives you a y value of 0, gives you an output of 0. That's one thing a y-intercept tells you, okay? It also tells you, if you graph the function, where the function will cross the x-axis, if you make a graph where it crosses the x-axis. But if your function is coming from some sort of setting, right, some sort of context, then the x-intercept may tell you something about that particular situation, right? So let's see what this version of this problem says. It says the number of defective items made by a factory worker is a linear function where x is the number of hours spent training the worker. So we would hope the more time the worker spends in training, right, the fewer mistakes the worker is going to make, correct? Okay, and that's true if you look at this linear function, right, because the slope is negative, correct? Right? So that tells me this linear function is going down. So as x increases, right, as the amount of training increases, the number of defective items is going to decrease, all right? Well, that's exactly the situation that we want, right? So here we're asked for what is the x-intercept and what does the x-intercept mean, okay? All right? So that's pretty straightforward once you've seen it, right? Okay? But If you haven't seen it before, sometimes you might be a little bit confused about what they're asking you. So here's our formula, right? D is equal to 4.5 minus a half times x, 0.5 times x, and we want to find the x-intercept, right? So that means we plug 0 in for the output, right? Don't plug 0 in for the input. That's going to give you the y-intercept, or in this case, the d-intercept, all right? So, but go backwards, right? So set the formula to 0 and then see if you can solve that equation. Well, this is a pretty simple equation to solve. We're going to practice harder equations later on today, all right? So I'm going to solve this one by adding 0.5x to both sides of the equation. So I get 0.5x to both sides of the equation. So I get 0.5x is equal to 4.5. And then, since I want x and not 0.5x, I'll divide both sides by 0.5, right? Okay? And you can get a calculator to help you with this, all right? And I think that's going to come out to be 9, right? So our x-intercept is 9, all right? So if we were made to make a graph of this curve, of this straight line, this is a line, so it would cross the x-axis at 9. But that's not the interpretation that we want to give, okay? So so x, I think, is 9. If I did that, if I solve that equation right, this is 9. But let's see, which one of these contextual interpretations for the x-intercept is correct? Is it C there? Right, okay, because when x is 0, right? I'm sorry, when x is 9, right? So in other words, when the training time is 9, the d value is going to be 0, right? And that d value means the number of defective items. So when the worker gets 9 hours of training, they don't get these defects, right? So so apparently that's how long we need to spend training our workers, right? And for this particular job, right? Okay. So don't put this as please don't put this as the answer, right? Okay. That's not the interpretation of the x-intercept. That's just the statement of what the x-intercept is. We've already said that up here, right? The x-intercept is 9, right? Okay. But that's not the interpretation of the x-intercept. What did I do there? Oh, did I not check my answer? Did I get it right? Yes. Okay. All right. Now, one thing you might want to do here is this is the next problem, right? So if you're looking for extra practice, right, remember you can always go back to these problems and ask for a similar question, okay? So that's a way of getting extra practice. So if you are having difficulty with a problem and you want to see more than one version of that problem, then ask for a similar question. These questions are algorithmically generated, so sometimes you'll get a different question. Sometimes the algorithmic generator is not that great and you won't get a different question. But here we did get a different question, okay? All right, so so there's a way of getting yourself some extra practice, okay? Make sure if you get it wrong the second time, make sure you save your best score right. I thought that was automatically would happen, but apparently you have to say that. All right, let me jump down here all the way to the end, okay? Because I want to look at the problem at the end, or a problem like the problem at the end. So this problem at the end is a linear regression problem. So we glanced at one of these earlier, but I just want to remind you where we're asked to take this table of data, right, and fit a line a fitting line to that table of data. So that is not perfectly, I don't think that's perfectly linear data, right? Okay, but we want to fit a line to that data, so we want to draw a line through that data that looks like that data, and then we can use that line to answer questions, right, about that particular situation, right, to make predictions, right, extrapolations about values for y, right, when x is, say, bigger than 90, okay, or when x is less than 50. All right, so we're not going to do this by hand, right? This is one where we're going to use the computer. And remember, to find that tool to do this regression, go back to your home page. If I can get the home page to open here. So your home page should look something like this, I hope, okay? And on that home page, there's an announcement that says linear regression tool, right? Okay, so you can open that, and then you can use that tool, right, to fit that line. So, of course, the data is in here as just an example. So what you will do is type over this data, okay? And once you've typed over this data, then you will get a scatter plot. You may not be able to see it very well because you may have to adjust the graphing window, but you'll get a scatter plot, and then you will get the formula for the regression line here. So it will tell you the slope of that regression line and also the y-intercept of that regression line as well. All right. So I think I've got this data or some data like this one somewhere in my notes. Yeah, here it is. All right. So this is a slightly different version of that problem. Okay. Maybe. I'm not sure. Maybe it's the same. All right. So to fit that regression line, right, you're just going to type these data pairs, right, into that, table. Let's see. So the first one is 5165 and then 6168. So let me go back here and see if I can type that in. So 50 and 165, and then 60 and 168, so you're just going to type over, right, these pre-existing values until you get all these typed in. Let's see, what's the next one here? 70 and 169, and then 80 and 170. So 70 and 169. So I typed that wrong. 70 and 169, and then 80 and 180. Oh, 80 and 170, right? And then 90 and 172. So this was supposed to be 170 and then 90 and 172. 90 and 172. And it updates dynamically as you're typing, so it's going to be changing that slope and the y-intercept there of your fitting line, okay? So apparently for this data, the formula is y is equal to 0.16 times x, and then plus 157.6, all right? So if I typed in the pairs correctly, then I could choose the answer, right, for that question, okay? So so remember, you can find that tool in the announcements, and then that makes it easy to plot that fitting line and then write down its formula, which is the key thing there. We can't see the fitting line because we don't have the right graphing window, right, for this table of data. So if I want to see the fitting line, I would have to adjust my graphing window. Let's try that just to see if we think we got this right. So let's try the x-axis from, say, 40 to 100. That would cover all these x values, right? And then let's try the y values from, say, 160 to 180, okay? So if you just go up to the wrench there, it will let you change the settings in Desmo. So let's see, I said for the x-axis 40 to 100, 40 to 100, and then for the y-axis, forgot what I said there, 160 to 180, something like that. That looks pretty good, right? Okay, so there's our scatter plot, and that orange line is that fitting line, right? Okay, so if we had done this by hand, we would have drawn a line that looks probably something like this, correct? Okay, but this is actually, in some sense, actually the best possible fitting line you can create for that set of data, the fitting line that has these coefficients, all right? Okay, so those are the things I wanted to just point out, right, about homeworks in general, but in particular for this section. All right, as part of our using straight lines, right, and setting straight lines, we're going to come across lots of equations that we have to solve. For instance, when we're looking for x-intercepts, we have to solve equations. And so let's take a little bit of a review of solving equations. All of these equations, or equations like this, you solve successfully. But I just want to remind us of how we go about this, right? So this is probably a little bit more complicated. Well, no, it's not. Okay, you may have problems in the homework that are very similar to this one. So let's see if we can solve this equation. The reason that that we're reviewing this type of equation in this section is, notice that in this equation, your unknown, which is x, obviously in this equation, right? It's just raised to the first power, just raised to the first power. Here you have x to the first power, and here you also have x to the first power. Equations like this are called linear equations because they're similar to equations for straight lines, right, where the x is just raised to the first power, okay? So that's why we're practicing these equations in this particular setting where we're talking a lot about straight lines. All right, so how would we go about solving this? What steps would we use to solve that linear equation? So what's the first thing? By the way, you know, solving equations, the solution steps are usually not unique. So there's sometimes more than one way to go about arriving at the solution to the equation. So I may show you one path that you want to take, okay, but you may do something slightly different on your homework, and that's fine, all right? But just in general, where would you start in solving that equation? Do what now?
Simplify the left side.
Yeah, we would simplify both sides of the equation, right? Okay, and that means just carry out the arithmetic operations, right, on both sides of the equation. So that's easy to do, right? I'm just going to multiply 3 times 2x minus 5, so that would give me 6x minus 15, right? You're going to distribute the 3 through the 2x minus 5, and then on the right-hand side, you're going to distribute that minus sign, correct? So minus x plus 5 becomes minus x minus 5, right? And now if you can, on both sides of the equation, combine any like terms that you have. So here you can add these constants together, and you get 5 minus x. So all I did there was simplify both sides of the equation, right? So that's often a typical first step in solving an equation. What next now? So from this point, what would we try? So add the 5. What do you mean add the 5, Uni? Did you say that? Someone said add the 5. What were you thinking? What's kind of your goal here? Well, yeah, all right. That's certainly the overriding goal, right? Okay. At the end here, we want to have something like x equals to some value, right? Okay. So how do I get to that point, though? Yeah, Montel, what?
So one of the ways you can do that is to take the negative 15, add a positive 15 to it, and then do the same to the 5 on the other side.
All right, so but the first thing you said is we want to get all the values like terms. In what sense do we want to combine the like terms?
Well, we want to separate them from each other.
So we want to separate them from each other. So which terms do we want to separate from others? Or which are the like terms, and you would say here in this equation?
We would put negative x on the other side, so we would have to add negative x. Add positive x.
So so you want to get so Nadine's suggesting getting the x's on one side, and what else, Nadine?
Add 15, and then you'll have to add 15 on the other side because whatever you do on one side, you have to do.
All right, so I think Nadine is just saying what you said, okay? She wants to get, so we're going to get the x's on one side, those terms on one side, right? The terms that involve x. And the terms that don't involve x, the constant terms, we're going to get those on the other side, okay? So, indeed, we're going to separate like terms. Like x terms on one side and constant terms on the other side, right? Okay? So Nadine's strategy for that is add x to both sides, right? Okay? So add x to both sides. And then, but also add 15 to both sides, right? Because that will get rid of the minus 15 on the left, and of course the x will also get rid of the minus x on the right-hand side, right? So let's see, what does this end up looking like? On the left we have 7x, right? And on the right we have what, 20? So we get 7x is equal to 20. Another way of thinking about that, by the way, is just moving terms from one side of the equation to the other. So you can think of this as just moving the minus x to the left and moving the minus 15 to the right. You can move terms around in equations from one side of the equation to the other as long as you change the sign when you move the terms. So if you move the minus x to the left, that will become plus x, and if you move the minus 15 to the right, that will become plus 15. So I end up here with 7x equal 20, and now that's pretty easy to solve from this point because, like Uni pointed out, I want to ultimately end up with x equal to something, right? Not 7x equal to something. So how do I get that to just x? Yeah, right. Just divide by 7, right? Okay. Right. So divide both sides by 7, right? And then on the left, the 7's divide out, so you get x, and there's our solution. There is 27s, okay? All right, so that's pretty basic algebra, right, in solving an equation like this, where you just have your unknown x raised to the first power. Now, we're going to encounter more complicated equations than this one, where we don't have x raised to the first power, and then things get trickier. But for now, okay, we can just follow these pretty simple algebraic principles, right, to solve that equation. All right, let me beef it up a little bit, though, okay? So let's look at this one, all right? Now, this one is a good one to keep in your notes because you're going to encounter problems like this in the homework, okay? And this will be one that you may find more challenging, okay? So you may want to write this one down, but in the homework, of course, you've got the help, right? But so you can also follow the steps in the help. I gotta warn you, though, the steps in the help may not look like the steps that I'm going through in class. They really are equivalent, but I may talk about it differently, or I may take the steps in a different order. So be aware of that, okay? All right, so this is still called a linear equation because it has the same property that that prior example had. The unknown here, which is t in this equation, is still just raised to the first power. This is t to the first power, this is t to the first power, and this is also t to the first power. So that is still a linear equation. By the way, if you move the t to the denominator, So if this were something like 3 over 12t, that would not be a linear equation, okay? Because t in the denominator is not raised to the first power. That's raised to the minus 1 power, all right, not to the positive 1 power. So, but that's not an issue here, right? T is in the numerator, so this is still a linear equation. But of course, what's ugly about that linear equation, so what makes it complicated to solve? Fractions, sure, right, yeah, it's got fractions in it, right, okay, so, and those fractions, of course, are always icky, right, okay, those always make our life more difficult. So, with that in mind, our goal here first, my first goal here is going to be to get rid of the fractions, okay, so I want to get rid of the fractions because I do not want to deal with an equation that has fractions in it, all right? So it's pretty easy to get rid of the fractions here, though, okay, in a legitimate way, all right? You can't just erase the fractions, right? But here's how you can eliminate those fractions, all right? So look, so we got 3 fractions here. One has denominator 4, one has denominator 3, and one has denominator 12. So we have fourths, thirds, and twelfths. If we were going to add, which we are not, but if we were going to add fractions together that were fourths, thirds, and twelfths, what common denominator would we have to use? So what I'm asking here is, what's the common denominator for those 3 fractions? You don't have to worry about this one. 12, right, okay. Yeah, so if you're going to add fourths, thirds, and twelfths, you would do that with a common denominator of 12, right? You would convert everything to twelfths, right? All right, so my common denominator here is 12. So what I'm going to do is not add the fractions together, okay? That would take a lot of work. But I'm just going to multiply every term in the equation. Make sure you multiply every term in the equation by 12, all right? So I'm going to multiply this fraction by 12. I'm going to multiply this fraction by 12. The 5 also must be multiplied by 12. And then I'm going to multiply that last fraction by 12. Every term in the equation, I'm going to multiply by 12. That does not change the solutions to the equation, but it will, of course, make the equation look different. So let's just do this. So I multiply 12 times t minus 2 over 4 minus 12 times t over 3 is equal to 12 times 5 minus 12 times 3 minus t over 12, okay? 3 minus t over 12. That looks like 3 times t. All right, so 3 minus t over 12. And you can already get a glimpse of good things that are going to happen here. What happens right here? That's right. The 12s cancel. So notice that that fraction has already reduced, okay? See, that's my goal. I want to get rid of the fractions. This fraction is also going to reduce because 4 goes into 12 3 times, right? So you can divide the 4 into the 12, and you get 3, and then times what's left is the t minus 2. And same thing happens here, right? 3 goes into 12 4 times, so you get minus 4 times just t, correct, right? And of course 12 times 5 is 60, so we end up with an equation that doesn't have any fractions in it. And now, see, that looks very similar to our prior example, right? Okay, by the way, be careful right here about this minus sign. When the 12s divide out, the minus sign is still there. So you have to write this as minus and then put the 3 minus t in parentheses. If you don't do that, you're going to make a sign mistake, and that's a very common sign mistake. So you're subtracting that entire numerator. So put the entire numerator in parentheses because you have to subtract that entire numerator. And now we're back to a type of equation we've already solved, right? So let's follow our steps from before. Let's see, Uni said first simplify both sides, correct? Okay, so was it Uni that said that? So I'll get 3t minus 6 minus 4t is equal to 60 minus 3 plus t, right? So let me see, 3t minus 4t is minus t minus 6, right? And then 60 minus 3 is 57 plus t, okay? And now, as Montel suggested, I've got to separate my like terms, right? So we want the t's on one side and the constants on the other side. And it doesn't, these are the constants. So minus 6 and 57. And it doesn't matter which side you move, which type of term to. So I'm going to move the minus t to the right, just so that'll become positive. And then let's move the 57 to the left. So I would get minus 6 minus 57, be sure to change that sign, equals t, and then when this t switches over, that becomes plus t. So we get what? Minus 63 is equal to 2t, or now divide both sides by 2, so t is minus 63 halves. There it is, right? So not a whole number solution, right? But still, there's our solution to that equation, okay? So that's a very important idea in solving equations that we use very frequently. If we have equations with fractions in them, since we don't like to mess with fractions, we're going to look for ways of eliminating the fractions. There are sometimes multiple ways of doing that, by the way, eliminating fractions from equations. But one possible way is what we did here. Multiply every term by a common denominator so the denominators all divide out, okay? And you end up with no fractions.
Is it like almost always used like this is like the best way to do it, or?
Well, so my recommended way is if you encounter equations that have fractions in them, think about how you can get rid of the fractions. All right. There are multiple ways, though, of doing that. Let me show you another way, Arthur. Now, this is a very simple equation, okay? But so we could solve that by inspection, all right? But don't rush, okay? Let's just think about that simple equation. That's an equation that has a fraction in it, right? Okay? So, again, my goal would be to get rid of the fraction, all right? Now, we could follow this technique to get rid of the fraction, but let me show you another idea we can use to get rid of the fraction. So we have this fraction equals 0, right? So that's kind of a special situation because the only way a fraction can equal 0 is if what part of the fraction is 0? See, suppose you have a mystery fraction. Suppose you have a mystery fraction here, right? Okay, and let me not use question mark. But suppose you have a mystery fraction here, and you just happen to know that that fraction is equal to 0, right? Okay? Then there's something, it got to be equal to 0. It couldn't be 1 or 2 or 3 or some other number. It has to be 0. But if you have a fraction that equals 0, then you automatically know something about that fraction, because how do fractions get to be equal to 0? The numerator has to be 0. That's right. The top has to be 0. It cannot be the bottom because, remember, you cannot divide by 0, right? Okay? So b cannot equal 0 just because you can't divide by 0. So we would know then that the top has to be 0. So you could immediately deduce, a has to be 0. But that equation doesn't have any fractions in it, see? Okay? So there's another way of getting rid of fractions out of an equation. So here we can immediately deduce, x must be 0, and there it's solved, right? Okay? All right? So that's a technique for getting fractions out of equations. Now, that seems like kind of a specialized situation, but that situation shows up a lot, okay? All right? So that's a very useful thing to keep in mind, all right? So that's just one example of another way you can get fractions out of equations. Well, all right, so we already saw an example like this one in the homework, right? Okay, so here we're looking for the x-intercepts of this. We're looking for the x-intercepts of this function, right? So We already know how to do that, right? Not the y-intercept. Y-intercept is easy. Just plug 0 in for x, right? But x-intercept means we have to set the formula to what? 0 and solve, okay? All right, so set the formula to 0 and solve. Oh, okay, Arthur. So here's another way I'm going to get rid of the. Here's another way I'm going to deal with an equation that has fractions in it. Okay. One thing we could try to do is immediately get rid of the fractions, right? Okay. We could try to immediately get rid of the fractions by finding a common denominator here, right, between 15 and 21, and then multiplying everything by that common denominator. Okay. Now, however, that's not an easy common denominator to think of, right? Those are kind of a little bit larger numbers than 3 and 4 and 12, 15 and 21. So it may take us a little bit of time there to find that, that common denominator for those fractions. But in this simple equation, I think we can proceed a little bit more directly, all right? So here's what I'm going to do. Let's move the 4/15 over to the other side. So that gives me minus 4/15 is equal to minus 2 over 21x, right? Okay. So see, that's almost solved already because that equation was so easy, right? That equation was so simple that we've almost got this solved. Because remember, we just want x equal to a number, right? Except I want this coefficient to be what, right? I don't want it to be minus 2 over 21. That needs to be obviously what? Yeah, I don't want minus 2 over 21x, Montel, in my solution to the equation, right? The solution would have to look like what? Just x equals to some value, right? Not minus 2 over 21 times x equal to some number. So I want to change this coefficient to, what's the coefficient of x here? It's invisible, but what is it? 1, right. I want to change that coefficient to 1. That's a 1x, right? I just don't write the 1 down, all right? Okay, so, but Joshua, you told me last time how to do this, okay? Because we solved an equation like this last time. To get rid of the 2 over the 21, right? Okay. You said what? I should multiply both sides by what? How do I get rid of the 21? Not multiply by 2. That's going to give me just 4 over 21, right? So, but let's concentrate on the 21. How can I get rid of the 21? Multiply by what? 21, right, yeah, okay. So you can multiply by 21, right, both sides. But then you would, so that will cancel the 21s, correct, right? But then you also have to get rid of the 2, Joshua. So how can I get rid of the 2? Well, multiply by what? Yeah, see, the 2 here is multiplied into the x, right? It's not divided into the x. So if I've got 2 multiplied by the x, how can I get rid of the 2 that's multiplied by the x? Divide, yeah, that's right. Divide by what? 2, right, yeah. Divide by 2, okay? Well, I'm going to do that at the same time I'm multiplying by 21, all right? I'm going to, at the same time, divide by 2. Notice that has the that's the same effect of doing what? Multiplying by the, what are we just multiplying by here? What? The reciprocal, right, okay? Just multiply by the reciprocal. Be careful about the minus sign that's here, though, okay? That's not going to go away yet, all right? So I can just multiply both sides by 21 over 2, okay? There's another way of getting rid of some fractions here. Multiply here by the reciprocal. So the 21s divide out and the 2's divide out, right? And you get minus x is equal to, and now I have this quantity on the left-hand side. 2 over 21 times minus 4/15. Ooh, I did something I told y'all not to do, right? I wrote two operators here side by side, multiplication and a minus. I hate that. So you cannot do that. So let's separate those by parentheses, all right? Never, ever put operators like multiplication and subtraction side by side. They have to be separated, okay? All right, now, so let's carry out that. So the multiplication on the right is easy, but the minus sign is going to stay there, so be aware of that. What happens on the left-hand side? Now, that looks harder, right? But it's not really that bad, all right, if you think about it correctly. Don't just haul off and multiply 21 times 4, okay, because that's going to make your life worse. You can do that. It's not a hard calculation. 21 times 4 is 84, right? But there's a shortcut you can use before you actually do this multiplication. Of course, 2 times 15 is easy also, right? That's just 30. But before you actually do the multiplication, notice this. 2 goes into 4, what? Twice, correct? Right? So you can divide the 2 into the 4 immediately here. And 21 over 15 will also reduce, because what number goes into both 21 and 15? 3. So you can divide 3 out of both of these numbers, and that would leave you 7 there and 5 here. So what you're left with is 7 times 2 over 5. This 2 is gone, right? Don't forget, though, the minus sign is still there. So what does that look like? I think that's minus 14 over 5, right? See how easy that was? By just having a little bit of foresight there, right? And thinking about what numbers divide out of the numerators and the denominators. Well, so now what I'm down to is minus x is equal to minus 14/5. I don't want minus x, though, right? I want positive x. So if minus x is minus 14/5, then I guess x is equal to what? Positive 14/5, right? So there's our x-intercept there, 14/5. So there's yet even a slightly different technique for solving this equation. This is why it takes a lot of practice with solving equations to get good at it, because sometimes different equations require slightly different methods to solve them efficiently, and you have to get familiar with what those different tricks are you can use in different situations. You can only do that through lots of practice. Well, you will get quite a bit of practice in this homework with solving these equations. Okay. All right. One place where we really like to give you practice in solving equations is in looking at word problems like this one. Okay. So some of these word problems are a little bit unrealistic, but though this one is not that bad. But some of the word problems are a little bit unrealistic. But the point of the word problems is to is twofold. It's to give you a little bit of practice solving equations. Okay. But also word problems help you understand just the basic ideas of algebra, okay? How algebra works, right? Remember, algebra always starts by picking a letter, right, to represent a quantity. Usually it's an unknown quantity, okay? And word problems are great practice with that idea, okay? Even though that's a very simple idea, students often need a lot of practice with that idea. It doesn't come naturally, okay? It's one of the things that makes algebra hard for people, even though it's a really easy idea. All right, so let's look at this problem and see if we can make sense of it. All right, so 4 office cubicles are going to be built from some prefabricated siding. You know what office cubicles look like, right? They look something like this, okay? And they're built by this prefabricated siding that can be combined in different ways, okay, to get different configurations. So if you go buy cubicles, you know, the company will, you know, it's going to ask you how much of this siding you need, okay? All right, so now in this particular, but the way we're going to build our office cubicles is we're going to build 4 of them, right? Okay, that have to be in a certain space. Okay, so we're going to build 4 cubicles in this big space, right? And the cubicles are all going to have equal dimensions. All right, now, the space available here, though, the total space available, we're told here, is 5 times as long as it is wide, okay? So this space that you're looking at is, this length is 5 times the width, okay? That's just how what that space is like, okay? Where we're gonna install the office cubicles, and we have enough money to buy 105 feet of this prefabricated siding like this, okay? So altogether, we can purchase 105 feet of this siding, but remember, we've got to get 4 cubicles out of that total 108 feet, okay, of siding that we can purchase. So the question is, what's going to be the dimensions now of each cubicle, right? So we want to fill up our space, and we can purchase 108 feet of this siding. So what would be the correct dimensions for each one of the cubicles, right? To use up all of the siding that we have, right, and fill up this space. Okay, so that's the problem. All right. So at some point here, I claim, all right, we're going to end up with some equations that we want to solve, right? Okay. And so we'll practice our equation solving skills. But before we get to the point of solving the equations, right, we have to write the equations down, okay? And equations involve unknowns, right? Okay. Equations involve unknowns. So what are the unknowns here, right? So what is it that we're looking for in this situation? So this is the algebraic practice. So just look there and see, what are you asked for, okay? Yeah, you're asked for the dimensions of what there, Kevin, each cubicle, right, okay? So these are cubicles, right, okay? So, you know, how do you express the dimensions of a cubicle like this, right? These cubicles are rectangles, right? So, yeah, you just give the length and the width, right, okay? So since I've got a picture here, and pictures are often helpful with word problems, since I've got a picture here, right, let's just see if we can fill that in, right? Okay. So we have here this width, right? Okay. Correct. So we need to give that a name, okay? So what do y'all want to call that width there? W. Yeah, sure, right? Okay. See, that is, you could have used Y or X or anything, right, that you want to pick there. That's, see, where algebra now has entered into the situation, because we're picking a letter there, right, to represent that unknown quantity W, that unknown quantity width, I mean, right? So any letter will do, okay? Now, also in this picture, you have this total space, correct? that is available for the cubicles, correct? Right? And so let's give that a unknown name as well, okay? So what do you want to call that? That would typically be called what? The length, right, okay? So there's the length, and again, let's pick a variable there to represent that quantity, all right? So what variable do you want to use? L, all right? Sure, all right? But you could pick X or Y or anything that you like, okay? All right, now, we also have a third here, unknown quantity, right, which is the size there, right? It's the length of each one of the individual cubicles. But if I know L, I can calculate that pretty easily by just doing what? Divide by 4, right, because we want the cubicles to all have equal dimensions, all right? So let's just stick with L here, which is that total length for a moment, okay? So that's the total length of the space that's available to us, all right? Now, okay, so I've written down now some variables there to represent my unknown quantities. That's an important place to start in problems like this. It also helps if you will write down exactly what your variables mean, okay? So remember, W was width, right, of our space, correct? That was the total space for the cubicles, and L was the length for that space. The reason it's helpful to write that down is because make that stick in your mind, right? What your variables stand for, what your unknowns stand for. Of course, it's pretty easy to remember that W is going to be width and L is going to be length. But in some situations, your unknown quantities are going to be a little bit more unusual, right, than length and width. And then it's really helpful as a reminder of what they're standing for to just write it down in words, okay? So you can really fix that in your mind. Now, look, so there are two unknowns that I need to, there are two unknowns there that I need to solve for, right? So eventually here I need to solve for W and I need to solve for L, okay? To solve for these unknowns, I'm going to need what? What now? Not close, okay, Furman. Not quite a function here, all right? But I do need something that's linear. I need a linear... What do you, remember I said I'm solving for these unknowns. What do you solve for unknowns? Equations, right, okay. So now what I need are to write down some equations. So I'm going to try to take the information that's given to me here, and I'm going to try to write down an equation or some equations, okay. All right. Just writing down one equation is probably a good place to start, okay, right? And then, you know, once we've got that under our belt, maybe we can get a little bit more ambitious, okay? All right, so let's see now if we can write down an equation, all right? So, where am I going to put that? I don't know if I have too much room here. Let me put it right there. So we want to try to use the information that's given to us to write down some equation. Now, some of this information I've already made use of, right? Well, no, I really haven't made use of any of my information, right? Okay, so so let's take that information that we're given and see if we can translate that into an equation. One thing that really sticks out to me, but other things may stick out to you, is this fact, okay? Because it's telling us very clearly, right, that the amount of siding you have available is 108 feet, okay? So you only have 108 feet there of siding available to you. So let's see if we can get that information into an equation. All right, so look, if I build this, if I build these cubicles, right, in this space where I have this length L, right, and this width W, how much siding am I going to need, okay? I know I've got 108, right, okay, but how much would that picture require of me? So to wrap those panels, right, around this big space, correct? And remember, you also have the panels in the middle because you have to divide the cubicles, correct? So how much of that paneling is that picture requiring of me? Can we just count it off? How much would this side require? How many feet? You don't know a number here, Montel, yet, right? Okay? But remember, this is algebra. So you can use a letter in place of a number, right? So it's not 30 feet, or could be, right? But I'm not sure if it's 30 feet. Yeah, Kevin, what would I say instead? W feet, right? Yeah, I need W feet, right? Okay. See, that's algebra, right? I'm going to use that letter to represent that quantity that I don't know yet, right? So this side requires W feet. What about this side, right? Once you put all the cubicles together, how many feet going to be required there? What? L feet, right? Okay, right. What about this side? W, and then this side again? L, right, okay? So let's put that, let's start writing down what we just said, okay? But we can't put it in words, right? So let's see. This side requires W feet, right? This side requires L. This side requires what? W again. And this side requires what? But I'm not quite finished because I have to separate the cubicles. So how much is that going to require? Well, I've already got here and here, so what else do I need? I need this side, right? And this side and this side. I'm going to have that to separate the cubicles. So how much is that, Skylar? We're going to have to institute, I really have been avoiding this, okay, but we may have to go to no PC policy. I may have to have you all turn those PCs off, okay, during class. So if you're not going to stay engaged with me, then we're going to turn them off, okay? This is not homework time, all right? Homework time is homework. That's why they call it there, okay? Class time is a different experience, all right, okay? So if I have y'all not being engaged with me here in class, we're going to institute that rule. So I'm going to give you this warning, okay? But next time it'll be new rule, all right? So Skylar, how many will I need here to create these sides? Because I've got to separate the cubicles, right? People don't want to be staring at each other while they're working. So what do I need there? Well, you just look at them there. How much panel, Skylar, for this wall? Kevin Teller, how much? W, right, okay? That's W feet, right? I don't know what W is yet, right, okay? But that's fine. I don't have to know what W is yet. My goal is to find W, okay? So I need an extra W. That's this one. What else? This one, correct? So that's another W. This one, right? So that's another W, right? So that is the amount that I need of the siding to build the 4 cubicles. But I only have so much siding available to me, right? So what does this have to equal to just because of the limitations that I have? What? 108, that's right, okay. So that has to add up to 108. Look, that is an equation, okay? That's what I'm looking for because it's equations that I can use to solve for these unknown values that I've already specified, correct? Let's see. So you can simplify that equation pretty easily, right? That's going to look like what? 5W, right? Is that right? Okay. Is equal plus 2L, right? Because I've got 2 of these L's is equal to 108. All right, that's great, but and that's a key start. Unfortunately, it's not quite enough because This equation, sadly, has how many unknowns in it? 2. Okay, right. I need an equation with 1 unknown in it, all right, because that's what I'm going to be able to solve for the unknown. So unfortunately, I made a great start, but I've got 2 unknowns here in this single equation. So that's unfortunately 1 too many unknowns in that single equation. So I have to see, is there some way I can eliminate from this equation, which is valid, can I eliminate one of these unknowns, all right? In a correct way, right? Okay, in a way that corresponds to the problem. What's the other piece of information that I haven't used here, though? What do we know about the total space available? It's 5 times as long as it is wide. So this total length, right, is 5 times what this width is, correct? That's the key, all right? So lurking inside the description was really another equation, and it was L is equal to 5W. So I really had 2 equations here, okay? That second equation is kind of so simple, it's easy to overlook. But that really is an equation. The length, right, is 5 times the width. And that's really the key that's going to help me solve this equation. Because now, instead of writing L, right, what can I write? I can write 5W, exactly, right, okay? So I can substitute here. So I have 5W plus 2 times 5W is equal to 108. And now there's an equation finally we can solve. And it's not that bad, right? That says 5W plus 10W is equal to 108. So that's 15W is equal to 108. And now just divide both sides by 15. So I think I come out with W is going to be, if you divide 108 by 15, I'm going to write that in decimal form, we get 7.2, okay? So the width there is 7.2 feet, okay, for each one of those 4 cubicles. Let's see if we can figure out what this is, all right, okay? Because remember, we wanted the dimensions of the cubicle, correct? All right, so what's the total? What's that total length on this side? It's 5 times the 7.2, right? What does that come out to be?
36.
That's 36, right. So this total length is 36. But remember, to get the cubicle, we're going to divide that by 4. What's 36 divided by 4? 9, right? So there we finally get it, right? There's the dimensions of each cubicle. It would be 7.2 by 9, okay? And then you would fill up your whole space, so you wouldn't be wasting any space in your office, and you wouldn't be overspending your budget for buying these panels, okay, that you're going to make the cubicles out of. All right. That's a very typical example of a word problem, okay? All word problems are slightly different, though, so I cannot give you a nice recipe for solving each word problem because they're all slightly different. And that's what students hate about word problems, because I can't give you a step-by-step method for solving them. But they all involve these 2 key ideas. I've got in my word problem, I will have some unknown numbers. I've got to write down letters, variables, to represent the unknown numbers, all right? Once I've got those letters written down that represent my unknown values, then I have to use the information in the equation, in the problem, to build equations, okay? Because equations are what are necessary to solve for unknown values, right? Okay? So from the information in the problem, I've got to write down some equations. But if you end up with an equation with 2 variables in it, right, 2 unknowns in it, you're going to have to eliminate one of the unknowns. So you're going to have to look for some more information like this that will allow you to eliminate one of the unknowns, okay? Otherwise, you won't be able to solve the equation, okay? All right. Well, we can look at more examples, but not today. But practice will also help you, and there are several word problems like this. They're going to result in linear equations in your homework, okay? So you'll get some practice in the homework doing this. Okay, all right, but remember it's due Friday, right? So, yes. As soon as I can get to it, I just haven't been able to do that yet. All right, I got to show you one more thing, okay? In addition to solving equations, we also are required sometimes to solve inequalities, which are going to work very similar to equations, okay, if you're solving a linear inequality. So linear inequality means the unknown is just raised to the first power, right? Just like in this example. An inequality is just a statement like an equation, except it involves an inequality mark. These are the 5 inequality marks: less than, greater than, less than or equal to, greater than or equal to. And then, less frequently, we'll encounter not equal, but that's an inequality mark as well. All right? The steps that you're using to solve equations, you follow the same steps for solving inequality, with one little exception, and I've got to show you that really quickly here. So let's solve this simple linear inequality. It's going to be like solving an equation with this one caveat thrown in, okay, that you have to be aware of. So I'm going to multiply 3 times 2x minus 3. That gives me 6x minus 9. And then, just like Montel says, right, I'm going to separate my variables from my constants. So I'm going to do it in this order just to show you something. So I'm going to bring the 6x to the right and the 2 to the left. Be sure you change the sign. So you have minus 9 minus 2 less than. The inequality stays the same. And then x minus 6x. So this is minus 11 is less than minus 5x. See, all of that's just like an equation, right? So far. By the way, all right, it's so much like an equation that one thing you have to be careful of is, and I do this frequently too, don't change the inequality to an equal halfway through the problem, because you're used to writing down equal marks, right? But you're not used to writing down inequality marks. So make sure if you start with less than or whatever inequality mark, you keep that through the problem, right? Don't make an equation all of a sudden. All right, well, this is pretty easy, right? How am I going to finish solving that inequality? How do I get rid of that minus 5? What? Yeah, divide by minus 5. Okay, Arthur, here's the one thing you have to watch out for. When you divide both sides of an inequality by a negative number, only negative number, positive doesn't count. But when you divide by a negative number, you have to reverse the direction of the inequality. So here's the correct solution to this inequality. I had to reverse the direction, but that's because I divided by minus 5. If you divided by positive 5, this wouldn't apply, okay? So divide by or multiply would also be the same. If you divide or multiply by a negative number, an inequality, you have to reverse the direction of the inequality. Otherwise, you'll get exactly the opposite solution. So our solution to this inequality is any number less than 11 fifths. Any number less than 11 fifths. So that's a big set of numbers. How do we write that set in interval notation? Any number less than 11 fifths. So if you write that as an interval, what set would that be? What are numbers less than 11 fifths? Less than 11 fifths. So here's a number line, right? Somewhere on the numbered line is 11 fifths. So numbers less than 11 fifths are where? To the left, right? Yeah, they're this direction, correct? So how would you write that set as an interval? Where does that set start? Negative infinity, right? Okay, and goes up to 11/5, right? So stops at 11/5, not including 11/5 because you only want numbers less than 11/5. So put a parenthesis beside the 11/5.
We don't put a parentheses around the infinity.
Yeah, you can never put, well, yeah, you put a parenthesis beside the infinity. You can't put a bracket there. So there's your solution to that inequality. Notice it's a big set of numbers. It's not just a single number. It's a big set of numbers, and that's what it looks like in interval notation. So when you're solving inequalities, you're going to get sets of numbers as your solutions, right? Okay? And be careful, again, multiply or divide an inequality by a negative number, you have to reverse the direction of the inequality. Otherwise, works very similar to equations. Well, at least if you have a linear inequality. If you have inequalities where the unknown is squared, things get ugly. Well, we'll have to get there later, all right? One step at a time here. All right, we're going to stop here today, so we're not going to have our after-class activity today. So Taylor gave you this sheet, so hang on to this until next time, all right? So don't lose that. And don't forget about your homework, right, that's due. Remember, when